Oh, that's how it happens to be. That is from the partial fraction decomposition. I did not go through the details of it. So you have to calculate C3, C4 and C5. Yeah. Okay, so you have to calculate these using the same procedure I used for the free response. It's just repetition of stuff. I'm not going to go through it. My notes will have the full solution. So this is u of t minus 2 times e to the power minus t e to the power minus 2t. Okay, so this is the net response, and I'm going to write the total system response in the next panel. I'll bring the board down so you can see the previous one. Okay, so x of t is x forced, which is u of t e to the power minus t minus 2t plus x free, which was 3 e to the power minus t minus 2 e to the power minus 2t, where the coefficients 3, 2, 1, 1 and 2 minus 2, all these things are obtained from the partial fraction methods. Okay? Be careful, do not combine the two yet. There are some common terms, but hang on to your horses. This is x forced x free. Okay? Now, I also want to write x of t as x transient and x steady state. Right? This is the other decomposition that we saw. How do I do that? Is first step, combine all the like-minded terms in the total solution. Okay, so look at x of t. So to do this, write x of t is u of t. I have minus 2 e to the power minus t, 3 e to the power minus t, so 3 minus 2 is mostly 1. I have plus 1 e to the power minus 2t, minus 2 e to the power minus 2t, so that's minus e to the power minus 2t. This is where I have combined the top two terms. Okay, I did not do it here because I wanted to see what was the forced response, what was the free response. Now to go to the next step, what is the transient response, what is the steady state response? I combine all the terms. Sometimes I can combine them, sometimes I cannot. In this case, I'm lucky. Transient terms in this solution is any term of the solution that vanishes as time goes to infinity. So what could be transient terms? Will this term vanish as time goes to infinity? The step input is always having a magnitude of 1, no matter what time is. So that's not a part of the transient response. Look at the next one. Does this vanish as time goes to infinity? Obviously it does, right? Does this vanish as time goes to infinity? Great news, it does. So those two are my transient response terms. So look at all terms of the total response which vanish as t goes to infinity, and so I see the culprits right out there. So the x of t is this is transient. X steady state of t. And I have two more minutes, so I'm going to take that. we define a stable system. Fundamental notion of any system is the following, okay? In the absence of forces, I come and stand in front of you. If nobody pushes me, what is my behavior if there is a gentle gust of wind? Probably not sufficient looking at my girth, but imagine it is strong enough to blow me apart. What is the effect of a gentle gust of wind coming and pushing me off? What do you think of that? Yes?
You won't like fall over to the right, it's going to be like pushed back against the wind enough where it's not going to push you over.
Let's say strong enough to.
Okay, you're just going to fall over.
Absolutely. I'm going to fall over. Because we are all inverted pendulums. So, when you look at a system, imagine the system in the presence of only input conditions. Does the system response go to zero as time goes to infinity? Such a system is a stable system. That is, if I am robust to initial disturbances, then I am a stable person. Right? My character is pretty strong. And that is exactly the criteria or the characteristic of a stable system. A stable system is a system whose free response goes to zero as time goes to infinity. It is robust to initial disturbances. It is robust to initial conditions. I'm going to write this down and then we're going to move on. So any system whose limit t tending to infinity, x free of t is 0. I'm going to elaborate on this in the next class with an example. Thank you.